I want to start by just talking about the problem, which is the vast majority of published models are not reproducible or reusable. And we've been trying to deal with that problem for quite a while, which I'll talk about. And also, we're discovering that many of the published models don't obey basic laws of physics. And recently, we've been trying to figure out how to provide a suitable framework. So for the first problem, we've been developing markup languages. There's several of them, and I'll talk a little bit about that in a minute, which are developed to help curate and annotate models and to encourage reuse with the ability to import suitably annotated modules. So trying to encourage a modular approach, building libraries of modules that people can reuse. But the problem is that these models still don't satisfy. That doesn't guarantee that the models satisfy the laws of physics, and hence the need for this possibly additional framework, which I'll talk about, bond graphs. So I'm going to talk about four things. The first is just a bit of background on CellML and the OpenCore software for use with authoring and solving CellML models. And then I'll talk a little bit about units, because I think units is critical to when you're engaging across different disciplines, and physiology is one of the few areas that involves every aspect of physics: electrical phenomena, mechanical, chemical, heat, etc. So it's by nature, it's a discipline that requires that you deal with processes that are crossing multiple physical spaces, and we've got to be able to make sure that we're handling energy appropriately across those, mass and energy across those different types of process. So then I'll talk about the key ideas behind bond graphs, which have been around for a long time, but only fairly recently applied to biological problems. And then I'll just indicate how this fits into a more three-dimensional, when you're dealing with anatomy and three-dimensional problems. So starting with CellML and OpenCore, the three components of this are shown here. So on the bottom left are the development of markup languages, which allow us to ensure reproducibility of models and that we can check for units and we can annotate and curate and so on. And that work is being led by David Nickerson. There's another group led by Herb Sorrow, SBML, and we work closely together with them. So Herb and Andre have both got a P41 from NIH, which is dealing with reproducibility. And then there's also another group, which is CellML, which is about the simulation, ensuring the reproducibility of the actual simulation itself. So specifying what solvers you're using, what tolerances, etc. But the models themselves are encoded in CellML and or SBML or NeuroML. And in a way, it doesn't matter much which markup language, because once you're in a markup language, you can translate to another one. And then the other part of this is the model repository. So you want these models to be freely available in curated, annotated form from a model repository, and that's called PMR, Physio Model Repository, at that website. And that work is being led by Tommy Yu at ABI in Auckland. And then finally, in order for these models to be useful so people can run simulations using them or author their own models, we've been developing a software package called OpenCore, led by Alan Garney, also at ABI now. And he's leading that work, and that website link there takes you to where you can download OpenCore. And I'll be illustrating some of the models I'll talk about with OpenCore. So first of all, CellML, which is about standards, the databases, as I've mentioned, and the tools. CellML.org is the website, so there's a lot of background information. The project's been going for quite a long time now. There's about 700 published models on the repository. There's about 1,000 models total, but a number are under development, so are in workspaces that aren't yet published. And these cover all aspects of biology involving lumped parameter or ODE or algebraic models. There is another standard called FieldML, which we also have developed for spatially distributed models, but I'm not going to talk about that today. So if you go to that website link for models at the PMR, you'll find you can download or in many cases, run these models directly from the website. So OpenCore is the software environment we're using, which is freely available. It's open source. It makes use of a lot of standard numerical solver libraries like CVODE, and it allows you to interface to the repository so that you can download models directly into OpenCore from the model repository, or you can develop a new model and then upload it to the repository. And it has facilities for curation as well. But it's got various links shown on the left side for managing files or obtaining files from the repository here. And on the right-hand side, links to help pages and to websites. But you can quickly get rid of those side panels and just reduce it to the environment where you're developing your own model. So here, for example, is an editing view of a very simple Lorentz model, a Lorentz attractor model. So the way that model would appear in CellML inside OpenCore would be, here's the ODE, and that if you hover over a particular line in the code, then you'll see the corresponding maths. So there's 3 ordinary differential equations, and you've set up variables, time, and 3 dependent variables plus 3 parameters. In this case, they're all dimensionless and they're given appropriate initial conditions or values. And then solving that gives you you can pretty flexibly specify how you want output, what you want to plot against what, and so on. So there's plenty of tutorials on this and help available, which I'll mention at the end. So I'm not going to spend any more time on OpenCore or CellML, but I just wanted to give you that background that we're now using for implementing the bond graph approaches. So now, before I talk about bond graphs, I'd like to talk a little bit about units, because I think as a community, we don't pay enough attention to units. I think they're really critical, for particularly, as I said, when you're crossing different physical domains. So if you think about the units that we use in science, there's 7 of them. The first 3 are joules, seconds, and meters. And they essentially define the world that we live in, the 4-dimensional space-time, and the fact that energy is the only quantity that's transferred between physical processes. And then we have various other types of entity that we deal with in the physical world we live in, and those are represented by these 4 additional units. So each of these 4 are essentially countable, the units based on counting individual particles. So in the case of the Coulomb, you're counting electrons, the charge on electrons. For Candela, you're counting photons. For moles, you're counting atoms. For entropy, you're counting probability states. So I think that's a good way to think about units. You've got 3 defining the world we live in, 4 the particular objects that we see in this world that we need to use as part of our physical processes. So, for example, in mechanics, you use joules, seconds, meters, and entropy. In electrophysiology, you typically use joules, seconds, and coulombs, and so on. So every aspect of physiology or biology generally is going to be making use of these processes based on physics that come back to these 7 units. And when you move across processes, the only thing that's common is the energy. And then just to set this in the context of SI units, the standard SI units are shown here: seconds, meters, kilogram, Kelvin, amps, moles, candela. But that's recently been changed, not the units themselves, but the way they define them. And in fact, last Friday, 2 weeks ago, was the end of the kilogram. So there's no longer going to be a kilogram held in a volt in Paris used to define the kilogram. It's going to be based on Planck's constant. So essentially the ones in bold are the ones that have changed, where the old units are being defined in terms of basic physical constants, Planck's constant, Boltzmann, etc. And I mean, amps was always a weird unit. The basic thing is coulomb, so it's now being defined in terms of coulombs. And Avogadro's number is another one. So the interesting thing here is that the units that we think are the right ones to be thinking about for setting up models are exactly the ones now that the SI committee has regarded as the basis for defining all the standard SI units, shown here with boxes around them, with the one exception that they're still using Kelvin rather than entropy. And Kelvin and entropy are pretty exchangeable. Entropy is just joules per unit Kelvin. So it probably doesn't matter too much which you're using. But I think it makes more sense to actually use entropy. Okay, so bond graphs. And I'll talk a little bit later about the main contributors to the development of bond graphs, but it essentially started with a guy called Henry Painter at MIT in the 50s who had appointments in electrical engineering, mechanical, chemical engineering, and he wanted to be able to talk to his colleagues in those different departments and realize that they're all dealing with the same entities to do with energy and power, but they had different ways of expressing relationships. But he developed this way of thinking about these all within one common frame. So the key starting point is the notion that blue line at the top is a bond, or it's a representation of transmission of energy or power. So there's no sense of, at this stage, of storage, dissipation, or anything else. That blue bond is just about transmission. But when you transmit energy, you're doing two things. You're dealing with a flow of some quantity per second, where that quantity is one of those 5 on the right, meters, or in the case of fluids, meters cubed, or it's coulombs, candela, moles, or entropy. So that's the substance you're moving along, but what you're moving is driven by a potential, and that potential is given in terms of joules per that quantity. So joules per quantity times quantity per second gives you power, joules per second. And that's the same across all these physical domains. So if you look at mechanics, the driving force, U is force, which typically is thought to be newtons, but it's much better to in fact think that it's really joules per meter. Newtons is just a derived unit. The base unit is joules per meter. Or if it's torque, it's Newton meters. Or if it's pressure, don't think kilopascals, think what is pressure? It's an energy density, so it's joules per meters cubed. And then the thing you're moving is either a velocity, meters per second, angular, or a volume flow rate, meters cubed. Likewise, electrical, typically we use volts, but really volts is a derived unit. What it means and how you define it is joules per coulomb. And the quantity you're moving is coulombs per second. So the product, again, is power, joules per second. Biochemistry, the driving force is a chemical potential, just joules per mole, and the thing you're moving is the molar flow rate, moles per second. The product, again, power. Heat flow, you're moving entropy states, moving probability states, distribution of atoms, particles, and temperature is a measure of that, and the driving force is an entropic potential, joules per unit entropy. And then the thing you're moving, flow rate. And I don't want to go into this one too much, but you could argue that a bit is another basic unit, whether you define it through Shannon in terms of energy or entropy rather, is a moot point. But whatever, the end result is that essentially the driving force is a information potential, joules per bit, and the flow is bits per second. So now let's get down to the guts of what bond graphs does. We're starting with this idea of transmission, and that transmission always has two adjoint variables. It's got a potential, which is the driving force, driving potential, and it's got a flow, and their product is power. But now we've got to think about the network topology, and then we've got to think about storage and dissipation. So first of all, network topology, and I'll give you examples of this in a minute. But what we do is to say that you have two types of fundamental node. One's called a zero node and one's called a one node. And everything that's to do with a zero node I've put in red or purplish, and everything to do with a one node is in blue-green. And the zero node quantity is a potential. So that's where you're going to define one of these types of potential depending on your physical problem. The one node is where you're going to define a flow property. And because a bond is uniquely defined by a potential and a flow, that means that all the bonds that are incident on the zero node have a potential U1. So I've put little U1s there on each of those bonds to indicate that. Whereas each of the bonds that are incident on a flow node, a one node, have got the value of that flow attributed to them, which is a V3 here. So that you can see why you have to alternate between zero nodes and one nodes, because a bond has got to be uniquely specified by its value of potential, and it couldn't have two potentials adjacent to each other or you'd have a conflict. Now, the next thing you do is, up to now we've been talking about transmission of energy, But now you need to think about what you do with energy, and you really only do two things. You either store it or you dissipate. And when you store it, you do that either statically through a capacitance or you inductively through a dynamic storage process. So for example, for mechanics, the static storage is a spring. For electrical, it's a capacitor. For chemical processes, it's the molar concentration, and so on. And then the dynamic storage, in the case of mechanics, it's inertia. In the case of electrical systems, it's the inductance, etc. And then all of them, of course, you're going to be dissipating energy, turning it into the entropy of the universe around. And so you need the ability to define a relationship between flow and potential that represents that dissipation. And in all of these white boxes where we're defining storage or dissipation, we're dealing with constitutive relations. That is, they're black boxes, despite being shown as white. They're black boxes which are representing some empirical statement of that relationship between potential and flow. Or in some cases, in the case of Q there, under capacitance, that's the integral of flow. In the case of inductance, the A is the acceleration or the rate of change of flow. But they're all in terms of that flow variable and the potential. So the next step, so we've got transmission, we've got two types of storage, and we've got dissipation. And then obviously we'll have boundary conditions, in some cases specifying values of variables. Now, here comes the really beautiful aspect of bond graphs. If you think about a zero node, what you're doing is you're saying that because we want energy to cross this node without loss, remember our only losses are occurring in a dissipative mechanism, a resistance, a damper or a resistor or a reaction, depending on the physics. This point here has to conserve energy. It's part of the transmission process. So energy is the product of potential and flow, but in this case, all of these bonds have the same potential. So we can take the potential U outside the sum, in which case we're left with the fact that the sum of flows has to be zero because potential is common to all of them, the same value. So essentially a zero node where you define a potential is a point where there's a flux balance. You're balancing mass or flux of some sort, that flow quantity. And it's, again, just coming back to energy conservation for that node. Likewise, with a one node, the thing that's in common is the flow. So all of these bonds have the same value of flow. So now I can take the flow outside the summation. So that means the sum of U's has to be zero. Sum of potentials is zero. And so the one node becomes the point where you're enforcing energy conservation or energy balance. And, pretty much that's it. That's the key concepts. But Henry Painter's insight into realizing that the laws of physics arise from basically these two ideas, a zero node or a one node, I think is the stroke of genius. And it's interesting when you look at if you Google Henry Painter and look at where he describes his insight into the one node in particular. It's very, very, very interesting. So at this point, we've got the sum of flows is zero. That means the flow in, V1, has to be equal to the flow out, V2 plus V3. And where V2 is defined as the rate of change of charge, because for a capacitor, you need to relate potential to the integral of flow, rather. And likewise, for an inductor, the relationship is with acceleration. So as well as balancing flow here, V3 equals V4 plus V5, we've got the fact that the acceleration is defined as the rate of change of that flux. And then the energy equation that drops out of the one node, we're saying that U1 coming in here has to be equal to U2 plus U3. So your energy and mass flux balance equations are just generated automatically when you think in terms of these variables. And that means that when you're formulating a model, you don't need to explicitly define these relationships. They come out automatically. So flux balance, you're dealing with mass, charge, or stoichiometry. Energy balance, depending on the physics, you're dealing with force balance, Kirchhoff's voltage law, or Gibbs free energy changes. And the other interesting thing about this, I think, is that it provides a very nice way of thinking about the structure of models, because one layer, your bond graph transmission layer here, is about the topology of the network, the stoichiometric matrix, for example, whereas here you're defining the constitutive relations. So this is the empirical part, and then your equations are dropping out, conservation laws are dropping out automatically from your bond graphs. But if you are now using a machine learning algorithm where you wanted to constrain the physics, what you would be doing is, and we do a lot of this now, is the machine learning is operating at the level of the constitutive relations, but constrained by the physics. Okay, and then if you look at this as a common framework for all of physics, this just shows the types of mechanism for static storage, dynamic storage, and dissipation for all these different types of physics. So you see all the usual relationships popping up: Ohm's law, Fourier's law, Fick's law, Goldman-Hodgkin, Katz, etc. But the lovely thing about bond graphs is it clearly identifies that these are all really just the same thing. They're just statements about dissipation, or about a relationship between flow and potential representing dissipation. And so you don't, in a sense, you don't need to think about all these different areas of physics as being different. They're all just part of a common framework where you happen to be identifying a flow in terms of coulombs per second if it's electrical, meters per second, or moles per second, etc., for different physics. And likewise, you identify your potential as being newtons, volts, or whatever you want to use, but they're all essentially representing that same concept of a joules per quantity driving force. Okay, now just a very simple example. Electrical network, anyone who's done an engineering degree knows, is very, very familiar with these sort of things. So now think of a circuit where you've got a capacitor, you've got some current coming in, there's a voltage across that capacitor, a voltage drop across the resistor, and a voltage drop U2 across the inductor. And these V's represent the current flowing. In a bond graph, that would appear like this. You've got your V1 coming in, V2 here is now disappearing into the capacitor with a relationship with the voltage drop here. The resistance is, dissipation is given by a relationship between the voltage across that resistor U3 and the current through the resistor V3. And the inductance, the coil, is, the inductance is L1, and the relationship is given in terms of the rate of change of flow of current. So now, so those are the quantities we're using: joules per coulomb and coulombs, or the different physical quantities for your empirical relationships. Capacitance, dissipation, or inductance have those units shown there, which look exactly the same in any system of physics, except you're just changing the quantity. So instead of coulombs, you might have meters or moles, depending on the problem. But otherwise, it's the same. So now the equations that drop out automatically, from here we know V1 equals V2 plus V3. From here we know that V3 equals V4 plus V5. And from here we know that U1 equals U2 plus U3. So those are the conservation equations dropping out immediately from the bond graph formulation. And now you can also see that an interesting thing is that the one node, the zero nodes in this case, are just really representing points in the circuit, but the one node is representing, in fact, the whole circuit, because it's dealing with the sum of voltage drops around the circuit. And in every case, in every type of physics, it's really interesting to see how the one node captures the key concept, whether it's Kirchhoff's second law, or it's Green's Gibbs free energy change, or it's Newton's force balance. It's always dealing with an energy concept, and it just reduces it to a single, a concept that's very easy to express once you get it in terms of bond graph term. So if we do a slightly simplified version of this to solve it, we just say that we've got an initial charge on the capacitor, and then put it into CellML form and solve it. You get what you'd expect in terms of dissipating a electron. You're exchanging energy between the capacitor and the inductor and dissipating it through the resistor. So there's two other concepts that become critical when you're dealing with energy movement between different physical systems. And the first one is the idea of a transformer. And the best way of illustrating this is a gearbox, because if you have a shaft coming in with a particular rotation speed and particular torque, and you want to produce an output which has got a much higher torque at a lower speed, lower angular velocity, then you do it by a gear ratio. So if we assume for the moment that there's no losses in here, and all we're doing is exchanging energy, we need to ensure that the product of these two equals the product of these two, because you're not losing energy, not losing power. So the transformer, that we're saying that the torque on the output is N, we've got a gear ratio of N, so the torque on the output is N times the input, and the velocity is faster by that same factor N on the input than the output, but the power stays exactly the same. So that's represented by a TF transforming factor and of N, and then the bonds here, the power here has to be equal to the power there, but you've got these additional relationships between the variables to ensure this conversion without loss of power across this system. And then a very similar thing happens with what's called a gyrator, which is where you're now transferring power, but it's between different physical systems. So now we've got electrical power coming in, we've got a voltage and a current, but on the output side, we're driving a motor in here, so we've got a torque and an angular velocity. But the product of these, again, has to be equal to the product of these. The power, we're not looking at dissipation at the moment. We can represent that separately. I'll show that to you in a minute. But the power's got to be equal. So again, there's the conversion constant, K, which is those units. The power is constant right across that system. The product of these has to be the product of these. So the Ks have to be such that, the relationships with K have to be such that, as shown here. So those are two additional things we need when we're converting energy. And it is actually worth making the point that generally, if you're using bond graphs, there's no huge advantage when you're dealing with a system that is only dealing with one type of physics. The real advantage comes when you're dealing with exchange of energy between different types of physics. But for biology, for physiology, that every system involves exchanging energy between different physical mechanisms. So it's critical that you deal with this issue of energy exchange and mass exchange. So here's another very familiar example, a voice coil. So now you have an electrical circuit with a battery, a resistor and an inductor driving a solenoid, a coil that's vibrating. So now you've got an electrical system coupled to a mechanical system. And your electrical system has a potential, so that's, in this case, we're just defining that as a boundary condition, the voltage. It's got a resistance with a relationship between the flow and the resistor, and the voltage rather, and the current. Likewise with the inductor. And the thing in common is the flux around the circuit, so that's the one node. When you look at your mechanical system, the variables now represent the displacement of the coil, and we've got both static storage through a spring in your coil, losses through a dissipative mechanism, and the inductance of the coil, and the coil sitting inside a permanent magnet. So the mechanics side says that there's a mechanical relationship between force and velocity, that's the spring, and so on. Sorry, that's the dissipation there, that's the spring. This one's your dissipator, you're losing some energy through friction there, and then there's a dynamic storage device. So that's the little bond graph around the one node for the mechanics. But then now they're coupled through a gyrator because you're exchanging energy, but again, the product of V1 and U4 has to be equal to the product of V2 and U5. So now we're defining U5 now as a mechanical force and U4 as an electrical force, a voltage. But now you can see the beauty of this is that from the electrical point of view, you have a back EMF, Faraday's law of induction, which says that you have a back potential here, which is related to the velocity of the mechanic system. So this V2 is a mechanical meters per second. This is a voltage, and the coupling is the field strength B and the length L coil. And then on the mechanic side, you have a force being produced, a Lorentz force. This is a voice coil is a Lorentz force actuator. And now the force being produced relates to the current. So now you've got an electrical term here, the flux, the current in the electrical circuit, giving rise through the field strength in the L to the mechanical force. So there's a complete symmetry between Faraday's law of induction and the Lorentz equation for force. And I think, if you don't think about this in von Graph terms, you would seldom think that these two things are really just the statement of exactly the same concept, but with different units representing the two different mechanical systems. So then power is preserved. As I said, you've got lossless transmission through here, and that's expressed here. And then these are the equations that drop out. So these have become the familiar voltage drop equations and force balance equations that you'd use for a voice core linear actuator. And if you solve that in CellML, OpenCore, you get, and I've done this, you can analytically derive these expressions and show that you're getting exactly the right solutions. So let's look at a biochemical system. Now we've got a chemical species, Q1, Q2, and a flux through a chemical reaction in terms of moles per second with forward and backwards rates. The chemical concentrations give rise to chemical potentials through Boltzmann's relations, and the flux through the reaction is given by a formula that's highly nonlinear. It's empirical, but it's unlike the electrical systems we were looking at earlier. Now you've got a highly nonlinear relationship, but that doesn't matter. There's no restrictions to linearity here. And the other interesting thing with a biochemical system is that the dissipative mechanism, which is your reaction here, is what's called a two-port device. So the reaction depends both on the U1 coming in and the U2 on the other side, but not as a difference, not as a potential drop, but explicitly on the two chemical potentials. So that's what the bond graph looks like for this system, with those units, and the equations drop out automatically. And then when you solve it in OpenCore, that's this based on starting with a concentration on one side, and which is falling off, and concentration on the other side rising. So a pretty simple example. Obviously, I've only had time to give a few simple examples, and we've done many models now in bond graphs across a wide range of physical systems. And if anyone's interested, I can send a much more detailed description of all of that. But I just wanted to indicate here on the linking with 3D models, because everything I've been talking about up to now has dealt with these lump parameter ODE algebraic type models. So now when you go back to your base units, and when you're dealing with spatial issues, you're dealing with continuum physics. So the units, meters, give rise to solid mechanics and fluid mechanics. So, and the two sets of equations you get out of that, exactly the same underlying conservation principles give rise to finite elasticity equations, where your constitutive relation is a relationship between a stress tensor and a strain tensor. Or in the case of fluids, it's Navier-Stokes equations, where you have your fluid density or viscosity as your empirical constants. In the case of heat flow and reaction diffusion equations, where you're dealing with entropy and moles, essentially the same equation applies to both, where the empirical parts now are this could be your ion channel source of current, this would be your diffusivity parameters. In the case of electrical systems or electromechanical systems, Maxwell's equations, dealing with coulombs and candela, and now the physical entities are shown again here in green. And for biological problems, those green highlighted parameters are where all the action is. Everything else is just the conservation laws of nature. But where the really interesting biology comes in is in these empirical relationships. So in fluid mechanics, you might want to relate the viscosity of blood to its rheology, to its biochemistry. And so you've got chemical reactions coming in here. In the case of soft tissue mechanics, you've got a lot of tissue structure coming into the definition, material properties of the components coming into this empirical relationship, and so on. So all the work at the level of lump parameter systems is really just to ensure, with bond graphs, is to ensure that you're getting relationships here in these green quantities which at the smaller scale, obey the laws of physics in the same way that you're imposing the laws of physics at the macro scale through Galerkin and finite element methods, which are a very nice way of solving these equations in a way that ensures conservation laws. So the bond graph is the complement in a way to the Galerkin finite element approaches to be able to ensure that you're dealing properly with the conservation of mass, charge, energy, etc. And I just to illustrate the idea that this is not just applicable to a point. A bond graph is not just applicable to a lump parameter system at a point. We're using it now, for example, for modeling circulation. So Sarush is a postdoc at the ABI looking at whole body circulation models formulated in bond graph form. And these are shown here in bond graph form, all available through the CellML site. And they run in real time, or better than real time. So you can be solving, so for clinical applications where you want to solve large scale CFD, you can do it easily on a desktop computer with a bond graph formulation of those equations. And then when you compare the solutions with the Navier-Stokes, you get extremely good agreement within a few percent, where the only area where you're losing something is where you're not properly representing some of the nonlinear inertial terms in the root of the aorta. But it's a very, very effective way of giving you an efficient way of solving fluid mechanics around the body. So I'll summarize now the overall key messages here. First is the idea that bond graphs provide this mechanism for properly ensuring that you define models that obey the laws of physics by thinking about a bond as a transmission mechanism where you've got both flow and potential, driving potential, based on units, on a small number of units that allow you to deal with any type of physics. And then you've got these various forms, mechanical, electrical, biochemical, heat flow, etc., which all can be represented via exactly the same quantities with just a reinterpretation of which unit you're making use of. And then this key notion of the zero node and the one node itself often relating to a property of the whole system, or that little segment of that system, and as for a circuit, for example. And then for further information about all of this, there's lots of information about CellML, the background, cellml.org, and all the 700 models, etc., are available on models.cellml.org. Bond graphs, as I mentioned, was pioneered by Henry Painter at MIT. It's been used in the electrical mechanical literature for people dealing with electromechanical problems in engineering for quite a while. There's quite a community there, lots of textbooks. The network thermodynamics, pioneered by Aaron Kachelski, came in later, and that's provided a more comprehensive framework that's applicable to biology. But the application of all of this to biology has really come from the efforts of Peter Corthrop, who's a guy that came out of the engineering electromechanics world and decided to dedicate the last part of his life to making sure that these concepts were coming into biology. So we owe a huge debt of gratitude to Peter Corthrop, I think, and also to Edmund Crampon. Peter's worked closely with Edmund, who's based at the University of Melbourne. So there's a whole series of papers from these guys and some of their students that apply bond graphs to various areas of physiology across all types of mechanism. I mean, one of the sobering things about this, of course, is that you discover that some of the things that you thought were absolutely sacrosanct, like Hodgkin-Huxley equations, turns out Hodgkin-Huxley equations dissipate energy in a completely illegal way. So you've got to reformulate them in bond graphs to make sure you're not losing energy if you care about energy production. But that's now possible. There's papers out that show how to convert your Hodgkin-Huxley equations into properly energy-conserving equations. And I just mentioned that bond graphs actually is the basis of Modelica, which is quite widely used in engineering. For OpenCore, and we're increasingly providing tools to allow the direct formulation of bond graph equations in OpenCore to make it easier to automatically generate the mass balance and energy balance equations. But for anyone that wants to explore OpenCore more, it's available at that website on the top left. And then at that website, you'll see the link to help, and there's very extensive help available on all aspects of use of OpenCore. And then down the bottom, there's a paper that we published that just details some of the architecture decisions for OpenCore. This work's been funded by some New Zealand sources. UK Wellcome Trust kicked off the first heart physiome fund. The European Framework 7 kicked off the funding through the VPH. And then NIH has played a major role through projects Dan Beard's Virtual Physiological Rat, P41 Centre, led by Herb Sorrow, University of Washington Centre for Reproducible Systems for Biomedical Modelling. And at the moment, of course, enormous thanks to the MAP core, the Spark MAP core, which is, I think, is an absolutely brilliant project and is helping us a lot with getting a lot of this framework into use across the autonomic nervous system. Thank you very much, and questions?
Hi, Peter. This is Grace. I was just wondering how bond graphs can simplify multi-scale models, and how would you address scales using bond graphs?
Yeah, that really interesting question. And it turns out to be an excellent framework for dealing with multi-scale issues, because what you want to do when you do multi-scale is you want to make, particularly when you do model reduction as part of multi-scale, you want to be able to ensure that as you move across scales, or you're reducing a complex model at one scale to plug into a higher scale, you want to make sure that you are conserving the physical entities appropriately. And where you're simplifying will be in the empirical statements. So by structuring your models clearly in terms of the structure of the model and then the constitutive parts, the empirical statements, you're actually making it a lot easier to see how you can do model reduction in a way that preserves the physics but simplifies often the way that you handle the constitutive description. So what might be a detailed physics mechanism at one scale, that may be subsumed into a more empirical statement of a higher level model.
And what about temporal scales, Peter?
But yeah, I mean, there will be equivalent statements. You will want to be able to treat different systems with different time steps or different time scales in a way that makes sure that again, that you're not violating any of your mass issues. I'm not sure I can answer that one any more explicitly than that at the moment, but it's certainly something on the table to be dealt with.
And well, finally, can you account for uncertainty within bond graphs?
Yes, because the uncertainty comes in the definition of your parameters, which are embedded into your empirical constitutive laws. So there's no uncertainty in terms of, I mean, you may have pathway uncertainty, you may have probabilities associated with particular pathways, but for a given pathway, you don't have any uncertainty in the physical statements of mass or energy conservation. Where the uncertainty arises is in the constitutive boxes. So again, bond graphs gives you a very nice way of being much more explicit about that uncertainty. And there's no reason you can't have probability distributions associated with parameters in your constitutive statements.